So in this section, we're going to talk through some of the major concepts in uniform circular motion. So this is the stuff you really need to understand. So to begin with, let's do some basic definitions. And we've kind of talked about a few of these things in the lab already, but here's the, the word for word definition that you can write in your notes and study and that sort of thing. So centripetal force, by definition, it is, for one thing you need to know, it's the net force. It's not one of those component forces. It's not normal force or gravity or tension or something like that. It is a net force, but is specific to something that is undergoing uniform circular motion. By the way, in uniform circular motion, what is it that's uniform? That's the speed. So the speed is the thing that's not changing in circular motion. We are also going to talk a lot about acceleration, and we'll talk specifically about centripetal acceleration. So this would be like any other acceleration that we've talked about. The thing that you need to understand that's different in UCM is that if something is undergoing circular motion, the acceleration always points towards the center of the circle. That's actually also true for the net force. So the centripetal force and the centripetal acceleration will always point towards the center of a circle. Another term that you'll find, and we'll use this in when we study waves as well, but we use the term period. Period has the symbol of, it looks like a capital T. It's a Greek letter tau, but it looks like a T, and the unit that it should be in is seconds. That's the SI unit for period. That is not just any time, but that's the time it takes to complete one full orbit for something that's in circular motion. So it's a specific period of time. That's why they call it period. So let's look at, this is a classic uniform circular motion proof that proves that the net force and the acceleration always point towards the center of the circle. So we look at a circle, and we can choose any 2 points along the circle to do this proof, but I picked a couple just because it makes a nice right angle. So let's say this is my initial velocity, and a second later the object is in the next position, and that'll be my final velocity. So what I'm going to do is I'm going to look at the change in velocity and assume that it occurs in a certain period of time. So I'm going to say that the change in velocity is going to be the final velocity minus the initial velocity. So I'm going to take those two arrows, which are vectors, and I'm going to subtract them. What you do when you subtract a vector is you actually change its direction. So instead of doing, so my first vector, I'm doing final minus initial. So there's my final. That's supposed to be straight down. And since I'm going to subtract the initial, I'm going to actually reverse its direction. So my initial velocity is going to be pointing to the left instead of pointing to the right. Notice that I added those two tip to tail. That you must always do that whenever you add vectors together. So if I look for my resultant, my change in velocity, I'm going to start where the first vector starts and end where the last vector ends. And so that arrow is going to be my delta V, my change in velocity. So if I take and I put that back on the circle in the middle, halfway between where those two original vectors were, no matter where I choose my initial and final velocity to be on that circle, the delta V arrow will always point towards the center of the circle. Notice I tried to keep it in the same direction that it started out being when I did my triangle over here, and I moved that over to my circle. It's pointing the same direction as it was on its resultant triangle, and so when I do that, the delta V points towards the center of the circle. So that's just change in velocity. I'm going to assume this occurred in some unit of time, so I'm going to say delta V over t, and that is going to be, you know that delta V over t is actually acceleration. So that's how I can say that my centripetal acceleration always points towards the center of the circle. Because of F equals ma, net force and acceleration are directly proportional to each other. That's not just in magnitude, that's also in direction. So if my acceleration points towards the center of the circle, my net force also points towards the center of the circle. That's something that when you do problem solving, you need to keep that in the back of your mind, because that will help you a lot as you try to figure out how to make a problem work. You have to always follow those rules. Acceleration, net force have to point towards the center. So here's my major concepts written as words, so it's something that you can look at and make sure that you understand these before you get to the test. So I already mentioned this, but centripetal force is the net force, it's not a component force. Both of them point towards the center of the circle. Always, always, always. The instantaneous velocity, so the velocity at any given moment, is actually tangent to the circle. The speed is constant, and we said that's the thing that's uniform when we say uniform circular motion. But remember that speed is a scalar. A scalar, this is from way at the beginning of the year, but a scalar, the direction does not matter in a scalar, but in a vector it does. So the speed doesn't change. So say something is moving at 2 meters per second as it goes around the circle. It could be a constant speed, but the velocity has to change because velocity is a vector. The vector has to have direction with it, and obviously the direction is changing as it moves around that circle. So those are the major concepts that you're going to need to make sure that you understand so that we can apply them in problem solving. And that's all we need to do on this one.